Now we're going to continue limit at infinity. Limit as x tends to infinity, it behaves like the highest power directly. It's 2x squared, which is infinity. Why? Because you can put for example 2x squared in factor, or x squared if you want. So it's x squared 2 plus 3 over x minus 1 over x squared. So it behaves like the highest power, because a number over infinity is 0, a number over infinity is 0. It's the same as 2x squared. So always when you have limit at infinity, it behaves like the highest power. For the second one, it behaves like 2x cubed. So it's 2x cubed. So it's plus or minus infinity. Here you have power of a power. So it behaves like 2x over 3x, highest over highest, which is 2 over 3. You can apply here Hospital's rule, but no need, because it's very simple to find highest over highest. Because if you do the derivative up, always we said 0 over 0, infinity over infinity, we can apply Hospital's rule. So here derivative is 2 over 3 directly, or highest over highest, the same. Here the highest over highest, 2x cubed over minus 5x cubed minus 2 over 5. If you want to apply Hospital's rule, as we said, it's very simple to do it directly. So it will be 6x squared over minus 15x squared. It's also infinity over infinity, or you can get rid of the x squared, so it's directly minus 2 over 5. Here it's highest over highest, so it's 3 over, I have cube down, so x squared and x cubed remains x down, a number over infinity 0. Here minus 3x squared over 2x, so minus 3x over 2, so it's a plus or minus infinity because x is up. You can apply Hospital's rule, it will be minus 6x over 2, so it's a plus or minus infinity. Here the highest power is 2x times minus 5x squared minus 10x cubed over x4, so it's minus 10 over 2x, a number over infinity 0. So always when you have a rational function for infinity, it's better to use highest power over highest power. However, when we're going to start by logarithm exponential, certainly we're going to use logarithm. The Hospital's rule is better, way better. Okay, but 0 over 0, always use Hospital's rule. Now piecewise function, we want to study limit and continuity. We have this function, it's x minus 2 if x less than 2, equal to 2, you have this one, and x bigger than 2. So to check if it's continuous, we need to find the limit to the left, limit to the right, and f of the point. If they are all equal, so it is continuous. If you do limit as x tends to 2 minus, in x less than 2, you have x minus 2, replace x by 2, it is 0. At 2, you have 4 minus 4, 0. And limit as x tends to 2, 2 plus, I mean here, you replace, you have 4 minus 4, 0 over 5, so it is 0. Since limit to the right equal limit to the left equal f of the point, so f is continuous at x equal to 2. For the second one, here, limit as x tends to 3 minus, you're going to have minus 9. 3 plus, also minus 9. But if you do limit as x tends to 3, you can see 0 over 0. 0 over 0 is undefined. So we say limit here exists certainly because left equal right, but it is not continuous. So here it is not continuous. Halla find parameter a so that f of is continuous at x equal to 2. So we have 2 minus, so it's 8a minus 6 plus 1. A plus, 2 plus, I mean, it's 4 minus 1, 3. And f of 2 is the same as this one. Nothing is going to change. So limit to be continuous, so 8a minus 5 must be equal to 3. So if you do it, so a will be 1. So here, if a is 1, this function f of x will be continuous. Now this part is only for GS students, not for LS. Extension by continuity. Consider f of x is continuous over a till x0 without x0, I mean here. And suppose limit as x tends to a minus f of x equal limit as x tends to a plus of f of x equal to L. Yani anywhere the limit here is L. Let g of x be f of x as we said for here, and equal small l if x equal to x0. So here, if you want to study the continuity, you need to study the continuity at x0. because limit as x tends to here, sorry, you must have x0 minus, not a, x0 plus. Since limit as x tends to x0 minus equal limit as x tends to 0 plus of f of x equal to f of x0, which is equal to L, here we said we have added something to the function so that the function will be continuous at x0. So this is what we add is called extended continuity. To understand it well, let us take an example. Suppose you had the function f of x equals sine x over x, defined for x not equal to 0. Extend f of x so that we have continuity at x0. Now we know that limit as x tends to 0 from last year of sine x over x, 0 plus or 0 minus, it doesn't matter, is 1. Hala, you can apply Hospital's rule. Why? Because it's 0 over 0. So derivative of sine x is cosine x, derivative of x is 1, and cosine 0 is 1 because we have it 0 over 0. You can apply Hospital's rule, but last year we took the property. So here, but if you want to do f of 0 to be continuous, it must be equal f of 0. F of 0 is 0 over 0 undefined. So we're going to do something so that it will be continuous. So what do we do? Let g of x be a function such that sine x over x, if x is not 0, it's continuous always. However, since limit to the left equal limit to the right equal to 1, so I'm going to say g of 0 is 1. So here now it is continuous, not f of x, but g of x. We extended f of x to a function in g of x to be continuous. For example, here we're going to say let g of x equals sine of x over x if x is not 0. But however, if x is 0, it is what? 1. In that case, limit as x tends to 0 of g of x equal f of 0, which is 1. So this is we call extended continuity. Hala, in number 2, can we extend f of x equal x minus 2 over x plus 1 so that it will be continuous at x equal, for example, minus 1? It's impossible. Why? Because no matter what do you do, if suppose you said g of x equal x minus 2 over x plus 1 if x not equal minus 1. Hala, you want to do it for x equal minus 1, you must have a number here and here must be equal. But if you do the limit up, limit as x tends to minus 2 over x plus 1 as x tends to minus 1, it is a plus or minus infinity. So we cannot have a number equal to plus or minus infinity, so we say we cannot extend it to be continuous. Okay, so this is the property of extending continuity for GS only. Thank you for listening.